Space and Science News with James. Welcome, science enthusiasts. Today, we're diving into a groundbreaking discovery that could revolutionize our approach to combating climate change. Imagine transforming the very gas that contributes to global warming into a clean, renewable fuel. That's exactly what researchers are achieving by converting carbon dioxide, yes, that notorious greenhouse gas, into ethanol, a sustainable energy source that could power our future. But here's where it gets truly fascinating. This isn't just another small step in green technology, it's a significant leap forward, made possible by an innovative catalyst that's changing the game. Today, we'll be talking about how scientists have unlocked the secrets of efficient CO2 conversion, because why not aim for ambitious solutions when the stakes are so high? But there's more to this story. This breakthrough has the potential to reshape our entire energy economy, creating new industries and transforming existing ones. So, what makes this catalyst so special? How does it work, and what implications does it hold for our planet? Let's dive deep into this subject of CO2 to ethanol conversion and uncover the secrets that could lead us to a more sustainable future. In a groundbreaking study, researchers at the Fritz Haber Institute have unveiled a novel method for converting carbon dioxide into ethanol, potentially revolutionizing sustainable fuel production. This innovative approach, detailed in the journal Energy and Environmental Science, could pave the way for more environmentally friendly and economically viable alternatives to fossil fuels. The research team, led by Dr. Arno Bergmann and Professor Dr. Beatriz Roldán Cuenya, has successfully developed a new catalyst that enhances the efficiency and selectivity of CO2 conversion to ethanol. This advancement marks a significant step forward in our quest for sustainable energy solutions and offers a promising route for green, cost-effective fuel production from CO2. The implications of this discovery extend far beyond the laboratory, potentially impacting global efforts to combat climate change and reduce our dependence on fossil fuels. As we face increasing pressure to reduce greenhouse gas emissions, innovations like this one provide hope for a more sustainable future, where waste gases can be transformed into valuable resources. Traditionally, the conversion of CO2 to ethanol has relied on copper-based catalysts under stationary reaction conditions. However, this approach has significant limitations in terms of selectivity and efficiency. The process often produces unwanted byproducts, reducing the yield of ethanol and complicating the purification process. Under demanding reaction conditions, catalysts can suffer from stability issues, diminishing their performance over time and necessitating frequent replacements. Moreover, the conversion process typically requires significant energy input, making it less economically viable and potentially offsetting some of the environmental benefits. These challenges have long been obstacles in the path to sustainable fuel production from CO2, hindering widespread adoption of this technology. To address these issues, researchers have been exploring various techniques, including pulsed electrochemical CO2 reduction, CO2RR. While promising, this approach has its own set of hurdles, particularly in maintaining catalyst stability under dynamic reaction conditions. The pulse technique subjects the catalyst to alternating periods of reduction and oxidation, which can lead to degradation and loss of efficiency over time. This cyclic stress on the catalyst material often results in structural changes and leaching of active components, further reducing its effectiveness. The Fritz Haber Institute team set out to overcome these obstacles by developing a novel catalyst design that could enhance both the selectivity and durability of the CO2 conversion process. Their approach focused on creating a catalyst that could withstand the demanding conditions of pulsed CO2RR while maintaining high selectivity for ethanol production. This required a deep understanding of the underlying chemical processes and innovative thinking in materials design. The researchers recognized that a breakthrough in this area could have far-reaching implications for sustainable energy production and carbon utilization strategies. The research team's breakthrough lies in their innovative catalyst design, which combines copper and zinc oxide in a unique nanocube structure. This novel approach offers several key advantages in the conversion of CO2 to ethanol. By adding a zinc oxide shell to copper oxide nanocubes, the team achieved increased ethanol production while minimizing unwanted byproducts like hydrogen. This enhanced selectivity is crucial for improving the overall efficiency of the process, as it reduces the need for complex separation techniques and increases the yield of the desired product. One of the most significant improvements is in catalyst stability. The zinc oxide coating acts as a protective layer, preventing the loss of copper atoms through oxidative dissolution. This significantly enhances the catalyst's durability under dynamic reaction conditions. In previous studies, the oxidation process involved in pulsed CO2 reduction was found to lead to the loss of copper atoms, reducing the catalyst's effectiveness over time. The new design addresses this issue by allowing the zinc component to primarily oxidize, sparing the copper and thereby maintaining the catalyst's integrity and efficiency. This innovative approach effectively creates a sacrificial layer that preserves the core catalytic functionality. Another key advantage of this new catalyst design is its ability to operate under less demanding reaction conditions. The researchers found that they could achieve similar or even superior ethanol production compared to pure copper catalysts, but with significantly lower energy requirements. This improvement in energy efficiency is crucial for making the process more economically viable and environmentally friendly. By reducing the energy input needed for the conversion process, the overall carbon footprint of ethanol production from CO2 is further decreased, enhancing its potential as a sustainable fuel source. The pulsed CO2-RR technique, combined with the CUZN nanocube structure, enables fine-tuning of the reaction pathway to favor ethanol production. This tunable selectivity is a major step forward in controlling the outcome of CO2 reduction reactions. The researchers utilized advanced characterization techniques, particularly operando Raman spectroscopy, to gain detailed insights into the catalyst structure and composition during the reaction. This allowed them to optimize the catalyst design for maximum efficiency and selectivity, providing a deeper understanding of the catalytic process at a molecular level. The team's findings support two crucial hypotheses in the field of CO2 electroreduction. First, they confirm that the metal oxidation state plays a critical role in the reaction mechanism. The ability to control and maintain specific oxidation states of copper and zinc throughout the reaction cycle is key to directing the production towards ethanol. Second, they demonstrate that active reaction species are created during the catalytic process itself. This in situ formation of crucial intermediates is fundamental to achieving high selectivity for ethanol. These insights are valuable for understanding the fundamental chemistry behind CO2 reduction and for guiding future catalyst designs in related fields. The innovative CUZN nanocube design leverages key principles of electrochemistry and materials science to enhance the selectivity and efficiency of CO2 reduction to ethanol. The catalyst undergoes alternating periods of reduction and oxidation during the pulsed electrochemical reduction process, creating a dynamic surface environment. This pulse technique is crucial for promoting the formation of key intermediates that favor the ethanol production pathway. The precise control of pulse duration and intensity allows for the optimization of surface conditions that maximize ethanol yield while suppressing competing reactions. During the oxidation phases, the zinc component of the catalyst primarily oxidizes, protecting the copper core from degradation. This selective oxidation is a key feature of the new catalyst design. By sacrificing the zinc oxide shell, the copper core remains active for CO2 reduction, maintaining high catalytic efficiency throughout the reaction cycles. This preservation of the active copper sites is essential for sustaining the catalyst's performance over time. The zinc oxide layer also plays a crucial role in modifying the electronic structure of the catalyst surface, influencing the binding energies of reaction intermediates in a way that favors ethanol formation. The interplay between the copper core and zinc oxide shell creates optimal conditions for ethanol formation while suppressing competing reactions. This synergistic effect is a result of the carefully engineered structure of the nanocubes. The copper provides the primary catalytic activity for CO2 reduction, while the zinc oxide modifies the local electronic environment and reaction kinetics to favor ethanol production. The interface between copper and zinc oxide creates unique active sites that are particularly effective for the multi-electron transfer processes required for ethanol formation. The pulse technique also promotes the in situ formation of species that are crucial for the ethanol production pathway. These intermediates, which may not form under static reaction conditions, play a vital role in steering the reaction towards ethanol rather than other potential products. The ability to control the formation of these key species through pulsed electrolysis is a significant advancement in selective CO2 reduction. By manipulating the pulse parameters, researchers can influence the population and lifetime of these critical intermediates, further enhancing the selectivity towards ethanol. The researchers used operando Raman spectroscopy to observe these processes in real time. This powerful analytical technique allowed them to monitor changes in the catalyst structure and composition during the reaction, providing unprecedented insights into the dynamic nature of the catalytic process. By correlating these observations with the reaction outcomes, the team was able to optimize the catalyst design and operating conditions for maximum ethanol production. The spectroscopic data revealed the formation and transformation of surface species, offering a window into the molecular-level events driving the catalytic conversion. This complex interplay of materials and conditions results in a more efficient and selective process for converting CO2 to ethanol, addressing many of the limitations of previous methods. The ability to fine-tune the reaction pathway through careful catalyst design and pulsed electrolysis opens up new possibilities for controlling the products of CO2 reduction reactions. This level of control is essential for developing practical applications of CO2 electroreduction technology, as it allows for the targeted production of specific high-value chemicals and fuels. The implications of this research extend far beyond the laboratory, potentially revolutionizing our approach to sustainable fuel production and carbon utilization. The efficient conversion of CO2 to ethanol offers a promising pathway for creating carbon-neutral or even carbon-negative fuels. This technology could play a crucial role in mitigating climate change by repurposing captured CO2 into valuable products, effectively closing the carbon cycle. By turning a greenhouse gas into a useful fuel, we can potentially reduce atmospheric CO2 levels while simultaneously meeting our energy needs, addressing two critical global challenges simultaneously. From an industrial perspective, the improved catalyst stability and lower energy requirements make this process more viable for large-scale implementation. The ability to produce ethanol efficiently from CO2 could transform various sectors, from transportation to chemical manufacturing. It opens up possibilities for creating a more sustainable and circular economy, where waste greenhouse gases are viewed as a valuable resource rather than a pollutant. This shift in perspective could lead to new industrial symbioses, where CO2 emissions from one process become the feedstock for another, significantly reducing overall carbon footprints. The potential for energy storage is another exciting aspect of this technology. Ethanol produced from CO2 could serve as a form of chemical energy storage, helping to balance intermittent renewable energy sources. This could be particularly valuable in grid stabilization and in providing a reliable fuel source for various applications, from portable electronics to vehicles. The ability to store excess renewable energy in the form of ethanol could help overcome one of the major challenges in transitioning to a clean energy economy, the intermittency of solar and wind power. Looking ahead, the research team is focusing on further optimizing the catalyst design and scaling up the process for practical applications. They are exploring ways to enhance the catalyst's longevity and increase the ethanol yield even further. Additionally, the principles discovered in this study could be applied to the production of other valuable chemicals and fuels, expanding the range of products that can be sustainably derived from CO2. This could lead to the development of a whole new class of CO2-based chemical processes, potentially revolutionizing the chemical industry. This breakthrough opens up new avenues for research in catalysis, materials science, and sustainable energy technologies. It challenges scientists to rethink our approach to chemical transformations and encourages the development of more sophisticated catalyst designs. The success of this CuZn nanocube catalyst may inspire similar innovations in other areas of green chemistry and renewable energy, leading to a cascade of advancements in sustainable technology. The potential impact on global efforts to combat climate change cannot be overstated. If scaled successfully, this technology could contribute significantly to reducing atmospheric CO2 levels while simultaneously producing a valuable fuel. It represents a win-win scenario in the fight against global warming, offering both environmental and economic benefits. The ability to turn a major contributor to climate change into a solution for sustainable energy production could be a game-changer in our global sustainability efforts. As we look to a future increasingly focused on sustainability and renewable resources, discoveries like this one from the Fritz Haber Institute play a crucial role. They demonstrate that with innovative thinking and rigorous scientific research, we can develop solutions to some of our most pressing environmental challenges. The journey from harmful greenhouse gas to useful fuel is a powerful symbol of the transformative potential of science in creating a more sustainable world, offering hope for a cleaner, greener future for generations to come. As we wrap up today's exploration into the groundbreaking conversion of carbon dioxide into ethanol, it's clear that this research represents a monumental step forward in our quest for sustainable energy solutions. The innovative catalyst developed by researchers at the Fritz Haber Institute not only enhances the efficiency of CO2 reduction but also opens up exciting possibilities for a greener future. By transforming a harmful greenhouse gas into a valuable fuel, we are taking significant strides toward addressing climate change and reducing our reliance on fossil fuels. The implications of this technology are vast. Imagine a world where our emissions are not just a problem to be managed but a resource that fuels our cars, powers our homes, and supports our industries. This breakthrough could pave the way for new industries centered around carbon capture and utilization, creating jobs and driving economic growth while protecting our planet. However, as promising as this technology is, we must remain vigilant and supportive of ongoing research and development. The journey from laboratory innovation to real-world application takes time, investment, and collaboration across various sectors. It's crucial that we continue to advocate for sustainable practices and support the scientists and engineers who are working tirelessly to make these advancements a reality. Thank you for joining us on this enlightening journey today. If you found this video informative and inspiring, please give it a thumbs up and share it with your friends and family. Your support helps us reach more people and spread awareness about important scientific advancements. Don't forget to subscribe to our channel for more exciting content on cutting-edge research, sustainable technologies, and the latest developments in the fight against climate change. Hit that notification bell so you never miss an update. We'd love to hear your thoughts on this topic. What do you think about the potential of converting CO2 into ethanol? Do you believe this technology can make a significant impact on our energy landscape? Share your opinions in the comments below. Thanks again for watching, and let's continue to explore the wonders of science together. Until next time, stay curious and committed to a sustainable future. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.